Hi, my name is Sean Emerson. My research focuses on using ferroelectric PZT films in conjunction with superconducting thin films to build memory elements for neuromorphic computing. The motivation behind this research is that as we find the need for more computational power, we're beginning to reach the physical limits of the components that we use in computers, meaning that we can no longer make our components smaller and instead we must scale up the whole architecture. As it turns out, this is not very energy efficient. So neuromorphic computing aims to solve this issue by modeling a computer architecture after the human brain, which is both compact and energy efficient. This project specifically focuses on the non-volatile memory components of neuromorphic computing. To display the application of ferroelectric films and superconductors in memory elements, we are working on building a device called a 9-pixel classifier, which takes 9 inputs and will hopefully be able to learn patterns in the inputs and then recognize those patterns at a later date. To do this, I've begun by growing PZT films, ferroelectric PZT films, on platinized silicon wafers and characterizing these films. An example of one of these films can be seen in Figure 1, while the hysteresis measurements can be seen in Figure 2. The loop seen in this figure displays ferroelectricity, meaning that the film will hold its electric field and can be switched back and forth with a delay. The next steps in this project are to build a synapse for the 9-pixel classifier. To do this, we will be using a sputtering chamber to deposit niobium on top of the PZT film. And once we've managed to do that, we will characterize the niobium and make sure that it is superconducting. Once we've gotten that to work and we can build a working synapse and we can adjust the resistance of the superconductor by adjusting the polarization of the film, we'll be able to start working on the pixel classifier. And the way the synapse should work is based on feedback from a program. It will polarize the film, the PZT film, one way or another, increasing the resistance or decreasing the resistance of the superconducting film. This in turn will give us various analog outputs depending on the input signal and the strength of it, which we'll then be able to use to learn and recognize patterns.